So we now turn our attention to a very interesting and important class of graphs called directed acyclic graphs or DAGs. So to motivate this class of graphs, let's look at a problem where we have a bunch of tasks to perform with some constraints. Suppose we are going on a foreign trip. Then of course we need a passport. We need to buy a ticket. We require a visa probably. We want to buy some travel insurance. We probably need some foreign exchange as well. And perhaps we want to buy some gifts for our hosts. Now, these tasks are dependent on each other in certain ways. Without a passport, you cannot buy a ticket, nor can you buy any travel insurance. For the visa, you need both the ticket and the insurance to be available. And without a visa, the bank will not give you foreign exchange. And finally, you would not like to buy gifts for your hosts unless the trip is confirmed. So unless you have all these things, including the visa in hand, you don't want to invest in the gift. So our goal is that given these constraints, in what sequence should we perform these 6 operations? Getting a passport, buying a ticket, getting insurance, getting a visa, buying foreign exchange, and buying gifts for our hosts. What sequence should we do it so that whenever we want to approach a task, the constraints that are required for that task are satisfied. So as you would expect, we will model this using a graph. In this graph, the vertices will be the tasks, and then we will have an edge pointing from T1 to T2 if T1 must come before T2. In other words, T2 depends on T1. You cannot do T2 unless T1 has been completed. So as an example, getting a passport must come before buying a ticket. So if T1 is getting a passport, T2 could be getting a ticket. Similarly, you must have a visa before you buy foreign exchange. Right? So there will be an edge from getting a visa to buying foreign exchange. So if we look at the constraints that we wrote, this is the graph that we had. Right? So we had a constraint which said you need a passport to buy a ticket, you need a passport to buy insurance, you need both a ticket and insurance to get a visa. So there are 2 constraints pointing to visa. Then you need a visa to buy foreign exchange. And finally you said we will buy a gift only if the trip is confirmed. And at some point at this stage, when all these operations are done, we can assume the trip is confirmed because nothing is blocking us getting on the plane, right? So this is a graph that we have, and now our goal is to sequence these 6 operations in such a way that whenever we want to perform a task, whatever it depends on has already been done. So we can see that you need a passport to do anything, so we always need to start with getting a passport. Now there is no dependency between buying a ticket and buying insurance as per the constraints we have so far. So after a passport, you can either buy a ticket first and then buy insurance, or you can buy insurance first and then buy a ticket. So there is a different ordering possible which does not violate the constraints. On the other hand, for a visa, you need both. Right? So visa must come after both ticket and insurance. But again, having done the visa, then there is no constraint between buying the foreign exchange and buying gifts. So you could do the foreign exchange before the gift or the gift before the foreign exchange. So there are, in this particular example, there are 2 possible ways of reordering the ticket and the insurance, and there are 2 possible ways of reordering the gifts and the foreign exchange. So overall, there are 4 different sequences which are compatible with these constraints. So this class of graph is an important class, and it has 2 important features. One is, of course, it is directed because these dependencies are from one task to another task. It's not a symmetric dependency, and there are no cycles. So if you had a cycle, it would mean that a group of tasks depend on each other. So there's no way to start because each task depends on something else in the cycle. So you have to break the cycle somewhere in order to get started, but you can't break it anywhere because each task depends on something else in the cycle. Right? So this graph will have directions on the edges, and there cannot be any cycles in this graph. So we call such a graph a directed acyclic graph. Right? So a directed acyclic graph is just a directed graph in which there is no directed path from any vertex back to itself. So if I start at any vertex v, it should not be the case that I can follow a sequence of directed edges in the same direction and somehow come back to v. So this should not be there. Right? So there should not be any cycle. We abbreviate the name directed acyclic graph as DAG. So very often, for simplicity, we will call these graphs DAGs. So the problem that we had addressed in our example is that we are given a set of tasks and we want to write them out in a sequence which respects the constraints. The constraints are nothing but the edges. So in general, we are given a set of vertices. These are our tasks abstractly, 1 to n. And we want to write out 1 to n in such a way that the constraints are respected. What this means is that we will write out a sequence of numbers which is a permutation of 1 to n in such a way that whenever there is a constraint of the form jk, that is, there's an edge jk, then in the enumeration that we have performed, j must come before k, right? So it cannot be that we have to do j before k according to our constraint, but in the sequence that we produce, k happens before j, right? So the order of vertices in the final sequence must respect the constraints given by the DAG. So for various reasons, this is known as topologically sorting the DAG. So the first observation is that if the directed graph had a cycle, then you will not be able to topologically order it. Because if it had a cycle, then for instance, supposing j and k are vertices on the cycle, then you will have a path from j to k and a path from k to j. Now it is easy to see that the topological ordering constraint extends to paths. That is, if I have j before k as an edge, I know that j must appear before k in the final sequence. Also, if there's the path from j to k, then there is a sequence of dependencies from j to k, so j must appear before k. Now, if I have a cycle, it says that j must come before k and k must come before j, so there is no way to break this dichotomy. So we will end up with a situation where we cannot order this set of tasks to respect the constraints. So if the graph has cycles, then it is clear that there is no topological ordering possible. So what we claim, however, is that for DAGs, that is, if there is no cycle, if the graph is actually acyclic, then we can always order it topologically. So the strategy is to order the vertices as follows. You first list all the vertices which have no dependencies. In our earlier example, the vertex which had no dependencies was getting a passport. We did not need to do anything before getting a passport, so we can do that first. Now once we have knocked off that dependency, you see any vertex for which all its dependencies are now satisfied, and then we can enumerate that. Okay, so we can systematically list out vertices with no incoming edges, then vertices all of whose incoming edges have already been accounted for in our enumeration, and so on. So to formalize this notion, we introduce some terminology. So recall that for an undirected graph, we use the term degree of V to refer to the number of vertices connected to V. So if V was connected by an edge to 4 vertices, then we would say that the degree of V is 4. Now since we have a directed graph, we have directions on these edges. We have some edges which are coming in and some edges which are going out. So we separate out the degree into the in degree and the out degree. So the in degree is the number of edges pointing into V, directed into V. The out degree of V is the number of edges pointing out of V. So our first claim is that every DAG has at least one vertex with in degree 0. In terms of our example, a vertex with in degree 0 is something which has no dependencies. Nothing, it doesn't depend on anything, there's nothing pointing into it. Now, how do we prove this? Well, supposing we start with any vertex V such that it has in degree greater than 0. Since it has something pointing into it, then it must have some edge coming into it. So let us call that V2. Now supposing this does not have in degree 0, then it must also have something pointing into it. So then I get a third vertex. So in this way, if I keep finding that the vertices I am encountering have in degree greater than 0, eventually I must enumerate all the vertices in my graph. Now if there is still not the case that the nth vertex, if there are n vertices, the nth vertex still doesn't have in degree 0, then it must have an incoming edge, but that cannot be from a new vertex, so it must point from one of the existing vertices which I have already seen before. Right? So therefore, if I have a continuous sequence of vertices, all of which are pointing into each the previous one with in degree not equal to 0, then I will end up with a cycle. But this is a contradiction because we have an acyclic graph. Right? So in any directed acyclic graph, there must be at least one vertex with in degree 0 which corresponds to a task with no dependencies from where we can start our enumeration of the tasks. So this is a more elaborate version of the algorithm that we described earlier. So we pick a vertex with in degree 0. Right? Recall that such a vertex has no dependencies. Now we enumerate it because it now has it's available for enumeration, and then we delete it from the graph. So when we delete a, a, a vertex with in degree 0 from a graph, so supposing we have a DAG like this, okay, so supposing we pick this one and we delete it, then clearly what remains is a DAG because it is still directed and we have not introduced any cycle. So it was already acyclic, and by deleting an edge we can't introduce a cycle, so clearly it's a DAG. So we can apply the same criterion. This new DAG must also have at least 1 degree with a vertex within degree 0, so we can enumerate that and keep going. Right? So we keep enumerating vertices within degree 0 until the DAG becomes empty. Each vertex we enumerate, we will delete from the DAG. So let us apply this strategy to this DAG. So we first begin by labeling every vertex by its in degree. So in red we have indicated the in degree of every vertex. So for instance 1 and 2 have no incoming edges, so they have in degree 0. Vertex 3 has 2 edges coming in, so it has in degree 2. Vertex 8 has 4 edges coming in, so it has in degree 4, and so on. Now we have to pick a vertex of in degree 0, enumerate it and eliminate it. So we have a choice between 1 and 2. So let's suppose we start with 1. So we start with 1, we eliminate it, and now when we eliminate it, we also eliminate the edges going out of it. So the edges coming into 3, 4 and 5 will reduce by 1 because the vertex 1 is gone. So if the edges coming into them reduce by 1, their in degree is also reduced by 1. So what happens when we eliminate 1 is that we enumerate it and we reduce the in degrees of 3, 4 and 5 from 2, 1, 1 to 1, 0, 0. So recall that before that the in degrees were 2, 1 and 1. Now these edges which are coming into them have been deleted, right? So when we delete this, we also delete the incoming edges. So now we have 1, 0, 0. Now we have 3 choices, 2, the original one which had index 0, and we have now 2 new vertices, 4 and 5, which correspond to tasks, if you want to call them, whose prerequisites have been completed. So task 1 was a prerequisite, only prerequisite for 4, task 1 was the only prerequisite for 5, it has been completed, so 4 and 5 are now available. So we can choose any of 2, 4 and 5, it doesn't matter. So let's suppose we choose 4, then again these 2 edges will go, so this will reduce to 1 and this will reduce to 3. So we can do that, we eliminate 4 and reduce the in degree of 6 from 2 to 1, the in degree of 8 from 4 to 3. Now perhaps we decide to eliminate task 2. So when you do task 2, then the in degree of 3 reduces and the in degree of 8 again reduces. So notice that 8 still has 2 pending requirements, namely 5 and 7. Okay, so it cannot be done yet, but 3 and 5 are available. So perhaps I do 5. So now 8 still has 1, and now I have no choice. The only task with in degree 0 is 3. So then I do 3. So now I can see that this is actually the way it is drawn is just a sequence. I must do 3 before 6, 6 before 7, 7 before 8. So I have no choice at this point. I must enumerate it as 3, then 6, then 7, and then finally 8. At this point my graph is empty and I have obtained a sequence of vertices which is a valid topological ordering, because every pair of vertices which occur as an edge in my original graph is ordered so that the source of the edge appears before the target of the edge. So let's look at some pseudocode for the algorithm which we just executed by hand. So in this particular algorithm, we first start by computing the in degree. So in order to compute the in degree, we need to find out how many, for a vertex I, we need to find out how many j satisfy the property that AJI is equal to 1, because this corresponds to an edge from j to I. So in an adjacency matrix, this corresponds to looking at the column containing I, because in the column containing I, we will have entries of the form A1I, A2I and so on, right? So we will have these entries and we want to scan all of these and then add up all the ones. So we start by setting in degree equal to 1, in degree I equal to 0, and then for every row j, we add AJI, so it's either 0 or 1, and so we therefore collect all the incoming edges which point into I as the in degree of I. Now we start enumerating. So we know this is a DAG, so we know there is at least one j with in degree 0 at every point. So we choose any such j, okay, choose a j which has in degree 0, enumerate it. Now when we enumerate, we want to eliminate it from the graph. Rather than going and actually modifying the graph itself, we will just work with in degree as a kind of approximate version of the modified graph. So we first set the in degree to -1 for this particular vertex. So -1 means it cannot be in the graph because you cannot have -1 edges point. You can have at least 0 edges or more. Right? So this effectively means that j is not going to be considered henceforth. And now for every outgoing edge from j, so wherever we have j pointing to k, we want to decrement this because we're going to eliminate this edge. By eliminating j, we eliminate this edge. So for every k from 1 to n, we scan all the outgoing neighbors of j, and if jk is an edge, ajk is 1, we reduce the in degree of k by 1. So what is the complexity of the algorithm? It's fairly easy to see that for this adjacency matrix representation, it's n square. As we saw, initializing the in degree itself takes time n square, right? Because we have one outer loop from 1 to n, and then for each outer loop, we have an inner loop from 1 to n. So this is an n square loop. And then when we enumerate the vertices, again, we have an outer loop which will enumerate every vertex once, okay? And then for the inner loop, we have to enumerate, check all its neighbors and decrement, right? So we have two n square loops, and therefore this whole thing takes order n square. Now we can, as we saw with BFS and DFS, right? If we use an adjacency list, we can be a little more clever, and we can bring down this time to linear. From n square, we can bring it down to order n plus n. So how do we do this? Well, we have these lists, right? So we have lists, say 1, 2, and for each of these, we have a list of its neighbors. So if we go through this, as we said, each edge in this, now this is a directed graph, so each edge is represented only once. If there's an edge from I to j, it will appear as an entry j in the list for I, right? So if we scan these lists, every time we see a j, we know there's an edge pointing into j, and we will increment. So we start off by setting all the in degrees to 0, we scan all the lists, and every time we see an entry in a list, we increment its in degree. So in one scan of the list, that is in time order m, we can find the in degrees. Now we have the list of in degrees, so we can put all the in degree vertices into a queue. This makes it easy to find which vertex to enumerate next. Okay? So at the end of this scan, we have done an order m scan to find all the in degrees. Now in an order n scan, we can put all the 0 degree vertices into a queue. Now we can do the rest pretty much as we did before. We enumerate the first vertex in the queue, and then we go to its list, which is now explicitly available to us in this adjacency list, its outgoing neighbors, decrement its in degree, and if any of those in degrees become 0, we can add it to the queue. So we know it is to be processed now. Right? So this becomes, overall it takes order m time to scan the list, it takes order n time to start the queue off, and then this is a loop of order n where across all the updates, we will overall update the in degrees order m times. So this is order n plus m. So here is the corresponding pseudocode, right? So the first step is to initialize the in degree to 0 for every vertex in our graph. Then we go through all the edges, right? So we do this by looking at each adjacency list. For each vertex, we look at each neighbor ij in the adjacency list, and for each of these, we increment the in degree of j, because we are looking at edges pointing into j, not pointing out of I. So this pointing into j will come in different lists, but as and when we encounter them, for each of them, we will account for them and add 1 to it. Now we go through the list one more time, a list of vertices, and every time we see an in degree 1, 0, we add I to the queue. And now we do this loop till the queue becomes empty. We know there's at least 1 at every point. Remember, as long as the graph, a DAG is not empty, we know there's at least 1 in degree I vertex with in degree I is 0. So it must be in the queue, because we added them all originally to the queue, and each one we generate, we will add to the queue. So as long as the queue is not empty, we take off the first element of the queue. Then we look at its adjacency list, decrement the in degrees of all those vertices, and if any of them happens to now become in degree 0, we add it to the queue. Right? So this becomes now a linear implementation of topological sort using adjacency lists and a queue to process the elements, because the reason why we need this queue is that otherwise, if we have to scan all the vertices every time to determine whether a vertex has become in degree 0, then that becomes an order n scan within this. So it becomes order n square again. So we need the queue to make sure that we don't spend time trying to identify the next vertex to enumerate. We don't have to go through all the vertices and check the integers. When we see the integer 0, we put it into the queue. So automatically it will come out without having to do any further check. So it gets absorbed in this order m work that we are doing here.